So I just want to take a break right now and talk about how what we've been doing kind of relates to Euclidean geometry in the Pythagorean theorem. Both matrix algebra and also covariant structures are firmly based upon this geometry and the Pythagorean theorem. Now, as you recall, the Pythagorean theorem simply states that c squared equals a squared plus b squared. You can remember that from your geometry class in high school. And this relates to a right triangle and states that if a and b are the lengths of the legs of the triangles and c is the length of the hypotenuse, then c squared equals a squared plus b squared. And the length of c is calculated by taking the square root of the sum of the squares of the other two sides. Now you already know this. This is right triangle. This is C, and this is, you can do A and B. Now, since a column vector of length n can be thought of as the coordinates of a vector in n-dimensional space, one can calculate the length of that vector by taking the square root of the sum of the squared elements in that vector. When a column vector is pre-multiplied by its own transpose, the resultant dot product is the sum of squares of the elements in that vector. So what in the world am I talking about? Let's start simply. Let's say we have a column vector of length n where n equals 2. So we can have, let's have 8, 6 as our column vector. And you can think of that as coordinates in since n equals 2, a two-dimensional space. So let me draw this out for you. Let's go back to geometry. This is our x-axis and this is our y-axis. Now let's say we have 1, 2, 3, 4, 5, 6, 7, 8 is right here. I'm just going to label these by 2's. And then 1, 2, 3, 4, 5, 6, 2, 4, up here is 6. Okay, so this could be thought of as you go over 8 and you go up 6 and we end up right here, which makes a right triangle, length 8 and length 6, and this is C. And here is, we can say this is A and this is B. So A squared plus B squared will equal C squared. Now we can calculate C by taking the square root of the sum of the squared elements in this vector. So taking the square root of 8 squared plus 6 squared. And we know, as I stated previously, when a column vector is pre-multiplied by its own transpose, the resultant dot product is the sum of squares of the elements. So it's going to look like this. Let's call this x. So we have pre-multiplied by the transpose. So 8, 6, 8, 6. This is going to equal 8 times 8 plus 6 times 6. And as you notice, we called 8a, so this is actually a squared, b squared, and it equals 100, which we know is c squared. So if we want to find c, we just take the square root of 100, and we get c equals 10. So the length of a vector, this length 10 that we found here, can be calculated by taking the square root of this sum of squares. This is the Pythagorean, or more precisely, the generalized Pythagorean theorem. That is, just as c squared equals a squared plus b squared, one can square and sum any number of sides, or vector values. So these are the vector values which we had as the sides. You can square those, and the square root of that sum is the length of the vector, so the length of 10 that we got here, And of course that's in two-dimensional space or n-dimensional space. So this is also closely related to variance, since variance is the sum of squares of the vector values, and the square root of variance is what? Yeah, it's standard deviation. Standard deviation is like the length of the vector. So notice once again we have c squared, which is 100. This is similar to variance. When we take the square root of that, you get the standard deviation, which is like the length. And the exact nature of this relationship will become clear in later chapters. But if you look on page 108 in your book, it gives an example with just more than 2 dimensions, which is hard to draw, which I can't draw. But you can imagine if we had, if we multiplied transpose of x times x, and we had larger value, more dimensions, like 8, 6, 5, 5, 4, 2, and once again this is from your book, 8, 6, 5, 5, 4, 2. So n equals 2, 4, 6. So this is in 6-dimensional space. Now, if you can draw that, I'll give you a high five. But I can't. So we know this is the sums of squares. 6 times 6 plus 5 times 5 plus 5 times 5 plus 4 times 4 plus 2 times 2, which equals 170. So this is like saying a squared plus b squared plus c squared plus d squared plus e squared plus f squared, and those are all sides, okay? And that will equal g squared. So if we want to find the length, we just take the square root of 170, so g equals square root of 170, which is 13.04 according to my calculations. And we can state that that is the length of the vector in 6-dimensional space for those vector values or sides. And once again, this also relates to variance, because variance is the sums of squares of the vector values, which is 170, and the standard deviation is the square root of variance, which is 13.04. Pretty cool, huh?